Okay, welcome to this lesson. We'll be looking at forces, mass, and acceleration in this lesson. I have a few outcomes, a few things I need you to take through during the lesson. The first one is to be able to state the relationship between force, mass, and acceleration, be able to calculate force using the correct equation, and deduce resultant force for various scenarios. I'll give you the scenarios, and you tell me what the resultant force is. Can you start off with your starting point, please? Look at each outcome statement. If you can do them already before the lesson, you put a tick in that space beside it at starting point. If you can do some aspects of it, but not entirely, it's a tick with a question mark. And if you can't do it, or you can only just barely do any of it, then it's a cross to start with. You use that to monitor what progress or not you make during this lesson. Okay. These are the things you ought to do on the specification. This is the AQA gsce specification P2. We will be looking at two outcomes. So, what a resultant force is and how to calculate it, we will take that off. About equal and opposite forces, we will take that off. We will do a few more things with that. We'll start calculating using F is equal to MA. But these are from the specification statement. I always start my sessions with the literacy. If you know what the keywords mean, then you would access the lesson a little better than somebody who doesn't. Have a look at these 4 keywords and let me see if you can define them. The first one is acceleration. What does it actually mean? What's a force? What's its mass? And what is resultant force? Right, hopefully you came up with these. Acceleration is the rate of change of velocity. Change in velocity in a certain time. The change in velocity, sometimes you see this equation in math. A is equal to v minus u divided by t. V is your final velocity, u was your initial velocity. V minus u is change in velocity. The word rate is indicative of time. Force, from key stage 3, is defined as a push, a pull, or a twist. But we'll add to it a little bit. An action that can change the movement of an object or its shape is a force. The mass is the amount of matter, amount of material that makes up an object, and it is measured in kilos. When you stand on your weighing scales in your bathroom, what you're actually measuring in kilograms is your mass. The resultant force is the overall force or the single force when several forces are added together, accounting for their directions. Resultant is net or overall force. We would treat forces in this unit as vectors. For example, an object which is going in the right direction is going from left to right with 6 newtons, and then it's given another force of 4 newtons. All you need here is the ability to add and subtract. If the forces are acting in the same direction, you add them. If they are acting in opposite directions, you subtract them, and so on. So, in this case, you need 4 in one direction, and then you need 6 more in the same direction. You would have moved overall 10 newtons in the direction from left to right. These individual things are called vector components, and the resultant vector is the addition, the net, well, depending on direction, maybe even subtraction, what you get when you resolve the individual components. Okay? In this case, you're moving 4 newtons from right to left, and you're moving 6 newtons from left to right. You move 4 spaces, and then you drag yourself 6 spaces in the other direction. What you would have done in the end is 2 newtons from left to right. 2 newtons is your resultant force. Let's have a look at some real-life scenarios then. Yummy apple. It's Newton all over. You've got a lovely apple. It's being pulled up by 3 newtons, and it's pulled down by 10 newtons. You are dragged 3 up and 10 below. Overall, you expect to see a net force of 7 newtons down. So 10 in the positive direction, I tend to use the big one as the positive. 10 in the positive minus 3, you end up with 7. 20 newtons to the left, 20 newtons to the right. It's a tug of war. Both sides are applying the same force. The object is not moving. It has a resultant of 0. Lovely chicken, by the way. Lovely chicken on the box. I like football, especially the phenomenal athletes you see on the pitch. Sculpted bodies, etc. And speed. The resultant force on this particular football is interesting. This is probably the first time that you see in 2 arrows on one side. You are always allowed 1 second to freak out when you see a physics question. Oh my god, I can't do it. And then that's it. You go back to logic. Okay, come on. That's the football. You've got 2 arrows going from right to left. In the same direction, like we said, you add them up. 6 plus 5, you get 11. And then you have a 4 going in the opposite direction. 11 take away 4, you end up with 7 newtons from right to left. Very hungry slug on the football. Hey, don't ask me how that happened. Okay. Again, 1 second, freak out. Oh my god, what is that? And then you look at it logically. Okay, let's look at left and right first. There are 2 forces here. There is 450 newtons and 350 newtons in the same direction, so you add them, you end up with 800 newtons. There is 800 newtons on the other side. 800 here, 800 in the opposite direction, equals 0. There is no net movement sideways. So we go to top and bottom. By now you should have noticed that forces tend to act in pairs. So we get left and right, and then top and bottom now. Forces going downwards, there are 2. There's 1000 newtons and 500 newtons. In the same direction, you add them, 1500 newtons. You have 400 newtons going in the opposite direction. 1500 take away 400, you end up with a resultant of 1100 newtons. If at this point you're not getting any of this, you need to rewind this lesson, slow it down, go back to the beginning, and work your way through it before you proceed any further. For those very lucky people who understand up to this point, we can start making more progress. Have a look at these few questions and let me see what you do with them. It's the same principle. If the forces are acting in the same direction, you add them. If they're acting in opposite directions, I tend to take the bigger one and give it a positive direction, and then you take away the smaller one. Did you get 10 newtons for the first one? If you did, well done. You're on a roll. What about the second one? Did you get 1 newton in that direction? Fantastic if you did. If not, go back a bit and work your way back to this point. Number 3 is 4 newtons downwards. Number 4 is 4 newtons upwards this time. And in number 5, there is no resultant, so the case ain't going anywhere. It stays exactly where it was doing what it was doing before. My grandmother's favorite car. Not exactly my taste, but I can see why she liked that sort of thing. It may probably have been the best thing she'd ever seen at that stage, but yeah. There are a few forces acting here. This car is moving, by the way. So weight is pulling it down towards the center of gravity. The cause forces acting in pairs. This is called reaction on this diagram. It's also sometimes called upthrust, depending on what textbook you pick up. The engine is doing some work, moving the car forward. That force is thrust. And the resistive forces that oppose motion, I am calling all of them with that collective term drag. The car would do certain things depending on the sizes of these forces in relation to each other. For example, if something freakish really happened and he drove into a tornado, the drag forces would become much bigger than the thrust forces. The car would slow down, and if the drag forces are big enough, they could actually stop the car. If they were really big, they could actually move the car backwards. Weight and reaction. Okay, we'll leave them alone for now. It would be interesting to see this man suddenly sink into the ground, but that's a figment of my imagination we'll leave for this time. So let's get to the business end of it. This is one of Newton's most famous equations. The resultant force F is equal to ma. F is equal to ma. Resultant force F is measured in newtons, mass is measured in kilograms, acceleration is measured in meters per second squared. You need to note these units. If you're given masses in any other units apart from kilograms, you've got to convert to kilograms first in order for this equation to work. Hopefully, from math, you know how to change the subject of an equation. If you do, you would find rearranging this equation, acceleration will become resultant force divided by the mass. Obviously, the mass would also be resultant force divided by acceleration. But just in case you're a fan of the triangle, I am not a fan of the triangle at all. Because if you don't know what goes into the triangle, it's of no use to you in an exam. But we'll do it just to pacify you for today. Force is equal to the mass times the acceleration. And whatever you use in looking for at a particular time, you cover that with your hand. If you cover mass, you would find force divided by acceleration. If you cover force, then you are left with mass times acceleration, and so on. Let's take a look at a simple question. Calculate the force required to cause a car of 1200 kilograms to accelerate by 5 meters per second. F is equal to ma. Let's see if we've got mass. Of course we've got mass. We've got 1200 kilograms as mass. We've got acceleration, which is 5 meters per second squared. You multiply them, 1200 by 5, and you get 6,000. It is force, so unit is newtons. Now this is what makes physics so easy. So easy to score points anyway. If you remember to put the units in, that is usually 1 mark. If you know how to substitute into an equation, that is usually 1 mark. And guess what? Pressing the calculator in the right way and get to the correct answer, that is worth another mark to you. They tend to be 2 or 3 marks, depending on whether you need to supply the units or not. Question 2. Have a go. Calculate the acceleration produced by a force of 200 newtons on a mass of 4 kilograms. You are looking for acceleration. You need to make acceleration the subject of that equation. So resultant force is equal to mass times acceleration. That means acceleration is equal to force divided by mass. Let me teach you a simple way to do this. Mass needs to move to the other side, so acceleration is left by itself. Mass was multiplied. When it crosses the equal sign, it does the opposite function. Opposite of multiplication is division. So acceleration is equal to force, which was there already, divided by the mass. So force was 200 newtons. The mass was 4 kilograms. Therefore, acceleration is 200 divided by 4, which is 50, and the unit is meters per second squared. Question 3. Easy peasy, isn't it? Calculate the force which accelerates a mass of 300 kilos from rest to 6 meters per second over a time of 3 seconds. F is equal to ma. Simple. I don't know. What do you think? Only problem is, where's the acceleration? So you've got to work it out. It hasn't been supplied. A, acceleration, is equal to change in velocity divided by time. Or, the mathematical representative, A is equal to V minus U divided by T. V, final velocity, was 6 meters per second. But it started from rest, which is 0 meters per second. 6 take away 0, you end up with 6 meters per second divided by the time it takes to cause the change, which is 3 seconds. So you've calculated acceleration, which is 2 meters per second squared. Now you can go back to the easy equation. You were looking for force anyway. Force is equal to mass times acceleration. Mass has been given. You've worked out your acceleration. So force is 300 kilos times 2 meters per second squared, and it's 600 newtons. Okay, now that you are an expert, could you have a look and let me see if you can copy and complete this table as quickly as you can. Remember that the mass has to be in kilos. If it's in any other units, you've got to convert. Right, how did you do? Did you get 24 newtons for the first one, in which case, well done. If not, you need to go back and work your way back up to this point. Did you get 40 kilos? And 20 meters per second squared? And 2 newtons? And 5,000 centimeters per second squared? If the last one was a problem for you, you need to go and look up your metric conversions. Okay, let's take a look at an actual proper GCSE style question. Remember, you are allowed exactly 1 second to freak out, and then you start reading the question slowly and carefully. The manufacturer of a family car gave the following information. Mass of car, 950 kilograms. It is physics, so I'm thinking the numbers are very important. The car will accelerate. It's a key word. I need to understand what that means. And it will go from 0 to 33 in 11 seconds. This is time t. This is final velocity v. This is initial velocity u. And the question is asking me to calculate acceleration. And thank you very much. You've actually given me the unit. So assuming I have absolutely no idea what to do, looking at the unit also gives you a clue. Meters per second squared means meters per second divided by second. A, acceleration, is equal to v minus u divided by t. Substitute into it. A is equal to 33 meters per second, take away 0 meters per second, divided by 11 seconds. A is equal to 33 meters per second divided by 11 seconds. You put that in your calculator, you end up with 3 meters per second squared. B. Calculate the force needed to produce this acceleration. F is equal to ma. We already have A, and m was supplied. F is equal to 950 kilograms times by 3 meters per second squared. Put that in your box standard average calculator. 950 times 3, and you end up with 2850. Okay, kilogram meters per second squared. What on earth is that? Oh, it's a force. What's the unit? If you don't know anything else, you know force is measured in newtons. Easy. We will look up this question in a subsequent lesson. For the purposes of this lesson, we will skip it. Okay, this is a simple quiz just to review where you are. If you don't need this section of the lesson, please stop and move on to a different lesson. If you want to review with this quiz, it's a good way to check that your basic knowledge is in. Which of the following is not a force? Let's think about that one for a second. Rotation. Don't know about that one. Gravity. Friction. Heat is a form of energy, so it's not a force. What units are used to measure force? I don't know. It could be in meters. Don't know. Kilograms, joules, Isaac Newton. Force is measured in newtons. Which force is an example of a contact force? Gravity doesn't touch you. Electrostatic. What's that? Magnetic. It doesn't need to touch you. But friction, you remember rubbing your hands together? Ooh, friction. You've got to have things touching or rubbing to generate friction. The amount of a material that makes up an object. I have already used this in the definitions at the beginning of the lesson. It is definitely not your weight. It is your mass. The upward force acting on a fish when it is swimming in water. Okay, there's friction in the water. I'm not sure if it's upwards. Gravity is never upwards. Thrust, that's questionable. Could there be a clue there? Up, thrust. If balance forces are acting on an object, what happens to the object? Can it change direction? Will it get faster? Will it change shape? It will have to continue moving at a constant speed, even if the constant speed was 0 at that time. If a ship is floating, the size of the upthrust must be. If it is floating, it is neither sinking nor going up. So what could it possibly be? It's got to be the same size as the weight of the ship. It's balanced and floating. If a man stands on a plank, the support provided by the plank is an example of, is it a resultant force? Non-contact force. That's an interesting one. Responsive force. We've not mentioned that one yet. It's a reaction force. Which of these four forces is only attractive? Magnetism, you have similar poles repelling, so it can't be magnetism. Air resistance, that's a funny one. Gravity always pulls you towards the center of gravity. One direction only attractive. Which situation involves friction that is not useful? When you strike a matchbox, well, you need friction for it to light. Friction between the shoe and your floor is what keeps you in one position, otherwise you'll be slipping. Air resistance flows the parachutist. Well, that's what you want a parachute to do. Friction between parts of a car engine is what you do not want. So, let's review this lesson very quickly. Look at the endpoint this time. Do you know the equation that links force, mass, and acceleration? If you do, well done. Can you calculate force using the correct equation? Can you deduce resultant force from various scenarios? I gave you the apple scenario. We looked at a hot air balloon. We looked at a few objects with forces. Can you resolve them? It's always a good point. At this point, it's good to do yourself a review. In my school, I call it Dear Diary. Dear Diary, today's lesson covered the basics of force, mass, and acceleration. I'm really good with the definitions, but I find X tricky. Or, I'm fine with everything else except the calculations. I need to action this by working through sample exam questions and so on. Good luck and see you next lesson.